Hey guys, welcome back to another A-Level Maths Made Easy video. This time we're doing proof by contradiction, which is the final set of proofs that you need to know. So there's a ton of different proofs that you have to know, proof by exhaustion and counterpoint and da-da-da-da. But this is a very specific type of proof. It's a whole kind of subchapter in the book, and there are a ton of questions that come up, and there's a very set method to it. But before we get into that, most of the people that watch these videos are actually not subscribed, so if you have ever found anything that in these videos useful, if you could please consider just clicking that subscribe button, it really helps me out. Not just that, but if you are interested in some of the tuition that I do, I have spaces in the A-Level Maths classes and A-Level Physics classes if you just go to my website for more information. And lastly but not least, my email address is also in the description if you want to email me any questions you have, if you want some advice or whatever, if you want to get in contact with me in any way. All of that's perfectly fine. So let's get straight into proof by contradiction. What the hell is proof by contradiction? Well, when you contradict something, it means that you essentially say the opposite of what happens. So when something contradicts, so for example, if I say I really like blue cars, but then my favourite car is black, for example, that's a contradiction because I said my favourite colour is blue, but my actual favourite car is black. There's a contradiction there. If I said, for example, it's not raining today, but then when I walk outside and come back in, I'm drenched, again, it's a proof by contradiction. Okay, it's a contradiction. And in order to do a proof by contradiction, there are 3 steps that you have to follow every single time. And the really annoying thing is when students don't do the first and or third step. So what is the first step? The first step always is you assume that the opposite is true, and you're going to write this assumption out. So in this first question here, it says use proof by contradiction. They'll always tell you, proof by contradiction, to show that there exists no integers x and y for which 6x plus 9y is equal to 1. So we're going to assume the opposite. So we're going to assume that x and y are integers that make this true. And that's it. So I'm actually going to make this a little bigger. But again, you assume the exact opposite. So again, they've said there are no integers x and y for which this is true. So we're going to assume there are integers for which 6x plus 9y equals 1. That's your first step. You get a mark. You get a mark just for saying assume the opposite. How cool is that? Step 2 is now you're going to go through this assumption and see if it actually works. Now we know that it shouldn't work because we're proving that it doesn't work. So if we look at this assumption, what could we say about it? How could we show that this doesn't work? Well, if I have a look at this, I have 6x and 9y. I could factorize out of 3. And in general, factorizing is a very good idea. And now if I have a look at this, I've got 2 integers adding to each other. So this would be an integer plus an integer times 3, and I get an answer of 1. That doesn't sound possible to me, right? Because I have 2 integers, I've added them together, okay? Then I've times it by 3 and get 1. Well, that's not possible. Let me show you why. If I divide both sides by 3 quickly, we have 2x plus 3y equals a third. Now, it's not possible for you to times an integer by 2 and add it to another integer times 3 and get a fraction, right? So I would then write, in fact, I'm going to copy and paste this down here, and this is step 3. There are no integers that will add to give 1/3. Therefore, the assumption is wrong. There are no integers x and y such that 6x plus 9y equals 1. That's the third step that a lot of students don't do. You need to write some kind of conclusion, and the conclusion has to imply the contradiction. So we're saying there are no integers that will add to this. Well, we've assumed that there are integers that will add to this, but we've just shown there are none, which means there are no integers x and y such that 6x plus 9y equals 1. Because when you assume there are integers x and y, you don't get a valid answer. You get something that doesn't make any sense. That's a proof by contradiction. The next major type of proof by contradiction is proof by contradiction that square root of a number is irrational. Now, the ones that have come up in the past, square root 2 and square root 3. they can give you basically any surd imaginable, but they'll probably give you square root of a number, and that's all they're going to give you. So how do you prove this? Well, an irrational number, well, first of all, what's step one again? We need to assume the opposite. So we assume square root 3 is rational. Right? We're assuming the opposite. Because you can't prove something's irrational. You have to instead prove that it's not rational. I know that sounds like the same thing, but it's not exactly the same thing. So what does it mean if square root 3 is a rational number? Well, a rational number can be expressed like so. A over B. And here's the key thing. Where A and B are integers. So they are whole numbers with no common factors besides 1. So what does this mean? It means that A over B cannot be simplified further. So as an example, I can express the number 4 as 8 over 2. I can simplify that to 4 over 1. So the number 4 is rational because I can the number 4 is rational because I can express it as 4 over 1, where the highest common factor of 4 and 1 is 1. I could also do the same thing for the number 3, because I can express it as, that's alright, 3 over 2 there. I can also do it for, let's pick a different number. Let's say a decimal, for example. Decimals are rational. I can express that as 5 over 2, and again, I can't simplify that fraction any further. So these are rational numbers because we can express them as fractions that can't be simplified further. 4 over 1 can't be simplified further. 5 over 2 can't be simplified further. You can even have it as something like 1.25. You can express that as 5 over 4. Right? You can't simplify it further. So we're saying that A and B are two integers whose highest common factor is 1. Well, let's go see if that's possible. So I'm just going to put this out there, by the way. These steps are very weird. If you do them once, you'll then know how to do it for any square surd number. You'll be able to do it for square root 2, 3, 5, 7, 11, etc. So all you really need to do is see me do this once, and then you'll be able to do it for literally any square root number, any surd number at all. So you'll be fine. But if I square both sides, have a look what happens. I get 3 equals a squared over b squared. Okay, now if I times both sides by b squared, I will explain why I'm doing this. Essentially, remember, this is wrong. We're trying to prove that this is wrong, that this can't be true. We're trying to contradict ourselves. We're trying to prove that this can't be true. So what I'm going to do is I'm going to see if the highest common factor of A and B is actually 1. Because if it's not 1, let's say the highest common factor is 2, or 3, or 4, or 5, then that means this is incorrect, which means our original assumption is wrong. Now if you see what I've done here, I get 3b squared equals a squared, which means a squared, and therefore a, is a multiple of 3. Logically, right? Because 3 times an integer squared is an integer, which means 3 times, let's say b is 1 for argument's sake. 1 squared is 1 times 3 is 3. 3 is a multiple of 3. Let's say b is 2. 2 squared is 4. 4 times 3 is 12. 12 is a multiple of 3, and so on. 3 times any integer, even if it's squared, will be a multiple of 3. So a is now a multiple of 3. We know that for sure. Wonderful. Which means we could write a as 3n, because it's a multiple of 3. Now if I sub that back into here, we get 3b squared equals 3n squared. And you can probably see where I'm going with this, maybe, possibly. 3b squared equals 9n squared. Divide both sides by 3, I get b squared is equal to 3n squared. Hang on a minute. 3 times an integer again. Well, that means that b squared, and therefore b, is a multiple of 3. Well, that means that A and B are both multiples of 3. Which means their highest common factor is not 1. It's 3. At minimum, it's 3. So that means they have a common factor of 3. Well, that contradicts what I said, right? I said A and B are integers where their common factors are 1. Only 1. Well, now we have common factors of 3. Therefore, this is a contradiction. So, common factor of 3. Therefore, assumption is incorrect. And root 3 is irrational. Now, I mentioned to you that you should now be able to do the same thing for square root 5, square root 7, and square root 2. And I would challenge you to try and do square root 2. Because the only difference is that instead of being root 3, it'd be root 2. And if you follow the logic along, we'll have 2 equals a squared over b squared, which means 2b squared is a squared, which means a squared is a multiple of 2, which means a is equal to 2n, which means b squared is also a multiple of 2. So you get the exact same result, where it's still a multiple of 2, which means the common factor is 2. If you do it with 5, you get the common factor is 5. Do it with 7, common factor is 7. So no matter what square root number they give you, it's the same process. It's just this is the only number that's different. It's the 3. Replace 3 with any number, and you can prove for that number it's irrational. But hopefully that makes a bit more sense. We've got 2 more, and honestly, these are probably the 2 harder ones. They're very difficult to explain, so I want you to bear with me, and they're very tricky to do. So for this one, it says, prove by contradiction that the sum of a rational number and an irrational number is irrational. So now we need to assume the opposite, and this is where the opposite becomes a bit weird, because what does it mean? Does it mean the sum of a rational and a rational number is? No. We're going to assume that the sum of a rational and irrational number is rational. So we're going to assume that the sum of a rational and an irrational number is rational. So what does that mean? Well, it means that my rational number, I'm going to express it as a over b, just like we did in the last question. My irrational number is just going to be a number. I don't know what the number's going to be. So I'm just going to call it c. It cannot be expressed as a fraction, though. Keep that in mind. And the answer should also be a rational number. So it makes sense for me to use, D and E? In terms of why I've used these letters, literally it's the first 5 letters of the alphabet, right? So the rational has to be 2 integers over each other. The next one just has to be a number, so I've just represented it as C. I don't know what the number is. And the rational number, again, has to be expressed as a fraction. So, okay, we're assuming that the sum of these two is irrational. Is rational, God. So, okay, let's take the sum of these two, right? Let's do A over B plus C equals D over E. This is where things are going to get a bit tricky, because it's very hard. If I, for example, if I do this sum, I'm going to get something that's legit. I'm going to get A over B plus CB over B equals D over E. And there's no way for me to show that that's wrong. However, I could show that C is not an irrational number. Because, again, think about what I'm going to get if I add these things together. I'm going to get a fraction. And a fraction is fine. It's a rational number. So doesn't that mean that this is true? It is rational? Well, again, I don't technically know, because C is an irrational number, and that's where it gets a bit messy. So the way I would prove this is I would instead try and show that C is not an irrational number. So for this to work, they all have to be rational numbers. That's basically what we're showing. I hope that makes a bit more sense, because it's very difficult for me to show that when I add these together, it gives me a rational number or an irrational. It's hard for me to show that when I add these two, the answer will be irrational. That's hard to do. But instead, if I show that C is not irrational, like I said it is, that's a contradiction. So instead, I'm actually going to rearrange this and do something like so. And of course, then it's just a matter of doing some algebra, so that's going to be dB over EB minus AE over EB, and that doesn't really make much of a difference. But what I do know is when I finish this, I'm going to ask you to take a second to pause the video and decide if it's a rational or irrational number. Well, if I have a look at this, and again I'm hoping you did pause it for a second at least, this is a fraction where everything isn't, well, first of all, everything's in a rational number. So two rational numbers times together gives me a rational number. So a rational minus another rational is rational, divided by a rational is also rational. So in other words, C is rational as it has been written, in the form A over B, where A and B are integers. Because remember, we said that A, B, D and E are all integers. It's only C that was an irrational number and therefore not an integer. So this is an integer minus an integer, or a rational number minus a rational number, divided by an integer / irrational number. So it must be a rational number. Therefore, you can say this contradicts our assumption. Hence, the sum of a rational and irrational number must be irrational. Now, I know some people are also going to say, well, hang on, if I actually work this out, I'm going to quickly do like an alternate reality, right, where we did this. So you would get, what would you get? You would get A minus BC over B, right? If I actually worked this side out. Because you times top and bottom by B in order to be able to add them together. Can't I then say, well, therefore this is irrational? And you would be right. But the problem is, how do you know that this is irrational? Well, you would say to me, well, a rational times, or even add, in this case subtract, an irrational equals irrational, right? So I agree, a rational times an irrational is always going to be irrational, but then you'd have a rational minus an irrational. If you say that's irrational, that's basically what we're proving. So you can't use what we're proving to prove the same thing. It's like when someone says, what does the word excitement mean? Oh, it's when something's exciting. That's meaningless. It's not a definition. In the same way that we can't say that this is irrational, because we have to use the fact that the sum, and again, don't forget, even though it's negative, it's still a sum, of a rational and an irrational number is irrational. So we can't use this fact, because that's what we're proving. Like, again, if you're trying to say, prove that 1 and 1 equals 2, you can't say, well, because 1 and 1 equals 2, 1 and 1 equals 2. That doesn't make any sense. It's circular logic. So that's why we couldn't do this part. So I said that it was a lot harder, and it is a lot harder, but it's also straight up impossible in this case, because we have to use the fact that we're trying to prove. Right? So that's another reason why we couldn't do it this way. Instead, we had to try and do it a bit of a wonky way. Let's move on to the hardest one, in my opinion, which is you're going to see it in 2 seconds. This question randomly came up one year, and there was no practice questions like it. So they can ask you to prove basically anything. So in my opinion, this is a matter of survival. These questions have been 3 marks most of the time. So you're looking at trying to get at least 1 out of 3. And the first mark, as usual, is assume the opposite is true. So you don't even need to know anything. Yeah, you don't have to do anything. You can get 1 out of 3, 33%, by just saying, assume that there are a finite number of prime numbers. So there's not an infinite amount of prime numbers. That's all we're saying. 1 mark. Done. So how would you prove this? That's a very good question. It is not the most intuitive thing in the world. But what we need to think about is, what is a prime number? A prime number is a number that has two factors, which is itself and 1. Yeah? Okay. So here's one way to prove that there are not infinitely many prime numbers. Prove that they're not a finite number of prime numbers. Let's say we have a list of all of the prime numbers in the world, right? P2, P3, ... all the way up to Pn, where n is the last prime number in this fictional world, right? Because again, we're proving by contradiction. We all know that there are infinitely many prime numbers. We have to prove it. Well, if I assume the opposite, that there is a limited number of prime numbers, I can therefore write a list of every prime number that exists. Logically. If there's a limit to them, I can list it. Okay. Then I'm going to say that x is equal to the product of every prime number in the world. Product of all prime numbers. So that's going to be P1 times P2 times P3 times ... times Pn. Yeah, that's what my number x is. So I've multiplied every prime number together. Now the interesting thing about this is this would not be a prime number because its factors would be the first prime number, the second prime number, the third prime number, the fourth prime number, the fifth prime number, and so on. Okay? So this is not prime because its factors are P1, P2, P3, ... all the way up to the last prime number. Okay, now let me think of another number. Whenever they talk about infinitely many, a really fun thing to do is to just say, well, what happens if I add 1? Okay, well, if I add 1, here's what I get. I get P1 times P2 times P3 times ... times Pn plus 1. Well, this is interesting because I can no longer divide this number by any prime numbers. Right? I can't divide it by any prime numbers, which means it's not a multiple of any number. So for example, if you think of multiples of 6, they are all multiples of 3, prime number. Multiples of 4 are all multiples of 2, prime number. Multiples of 10 are all multiples of 5, prime number. So what I'm saying here is, so essentially if you can't divide a number by any prime number, it must be prime in and of itself. Crazy thought, right? So, y cannot be divided by any prime number, as there will be a remainder of 1. So, the only option, well, there's two options technically. So either, whoa, careful, either y is prime and therefore the assumption is incorrect, which means it's proof by contradiction, or y has a different prime factor that we did not list. So in other words, my list here was incomplete, but I told you it's the product of all prime numbers. So I couldn't have missed one, but that's the only two options, right? Either y is a prime number, in which case this list is incomplete, or it has a factor that we didn't list, which means this list is incomplete. Either way, so regardless, the assumption is incorrect. Right. Therefore, there are an infinite number of prime numbers. And balance is restored to the universe because, of course, that is 100% true. There are not an infinite number of... Sorry, God, there are not a finite number of prime numbers. The double negatives really get me sometimes. But once again, it's always 3 steps. So why did I pick these questions? Well, I picked the last question because I thought it was a very difficult one. In the actual exam, very, very few people, I'm talking about a fraction of a percent of people, managed to get 3 marks on this. It's really, really rare. Bearing in mind that people have done this proof, actual mathematicians. The first people to do this proof were PhD candidates. Like it's not easy. In terms of the other questions, so for example, this one here, they put some kind of spin on this. So they might say, prove that the sum of 2 rational numbers is rational, or prove that the product of a rational and an irrational is irrational, or whatever. But it's the same process that you're doing. Likewise with this is really, really common, and they can ask you about the square root of basically any number that isn't, well, not 4, right? That isn't a square number. So square root 7, square root 11, square root 10, etc. And you follow the same steps. So super useful. And of course, the very first one I picked because I think it's a very nice intro. It's not too tricky, but again, they could also give you variations on this. They've done that a couple of times where they just change X and Y. Why not, right? It's the same type of thing. But proof by contradiction is very tricky. Hopefully this gives you a bit more of an intro into it and you can perhaps attempt some more questions. Once again, if you did find this useful, please consider subscribing. Website in the description for tuition and all that fun stuff, and then my email as well in case you have any questions about whatever it may be. So some people email me about university applications or whatever. I'm open to anything and I do respond to it reasonably quickly. But other than that, I'll see you in the next one.